morning, ladies and gentlemen. Thank you very much for inviting me to present here a part of the research in the composites group at the University of Leuven, which is related to the subject of today. My co-authors are Ignaas Verpoest and s.r.o. And just a word about the group. So we were 16, we are in 17, about 50 people in Leuven. The group started in '82, which is already 35 years ago. And we have, well, it's appropriate to use the Olympic rings here in Athens, of course. We have 5 topics in the group. Ignaas Verpoest, as a postdoc researcher, works on composites on micro and nano level. Stefan Lomov, who is now the coordinator of the group, works on composites on macro and meso level. Then we have 2 people in the other campus of our university, campus in Brugge and campus in Mechelen, who work on processing and product development. David Sereno, who joined a couple of years ago, works on physical chemistry of composites, and Art van Vuren works on natural and bio-based composites. So what is the problem statement of what I want to present today? Well, we all know, I don't have to convince you all that carbon fibers are fantastic materials, high stiffness, high strength, low density, and here they are in this banana-shaped curve, as we all know it, the absolute stiffness versus failure strain. And so they have a fantastic stiffness, but they have a rather poor failure strain. And many other polymer-like materials are at the other side. They have a very low stiffness and a very high, or can have a very high failure strain. Glass fibers are somewhere here. Now, this low failure strain leads to sometimes accidents. If you have a very expensive carbon composite car, you really don't crash it. But similarly, and that's something we are working on now with a spin-off company of 2 of our students, Reinforced, who have invented a method to make carbon fiber bikes not break suddenly in a brittle way anymore. But similar things, if you watch Formula 1, it's sometimes nice to see how these cars crash and then the carbon fiber parts splinter in all directions. So, what are the possible candidates to make these carbon fiber composites tougher? Well, first of all, we could look at steel fibers. And take care, this is now the banana-shaped curve, the same one, but here we have replaced the absolute stiffness by the specific stiffness, taking into account the density of the material. And then steel is here, and steel has a very interesting property in the sense that, of course, it's very stiff, but it's also very heavy, but it allows you, and myself being a metallurgist by education, we all understand that steel can be very brittle or can be very ductile depending on the composition and on the thermal treatments, which is not possible with carbon. Carbon remains brittle, we can't do almost anything about it. So here we have a potential of adding steel fibers to composites, and the spin-off company I was talking to you about, Reinforced, they have been developing a system where they hybridize steel with carbon fibers. I will not further go into that. Another candidate is drown polypropylene. So polypropylene fibers are tapes which are tough, which are very light, have a density of 1, but they are not very stiff. And the question is now, and this is this concept which leads to the self-reinforced polypropylene composites, where you take either highly drowned polypropylene fibers or tapes, and depending on different processes, but one of them is that you melt the surface of these reinforcing fibers or tapes, you compress them, and you get a polypropylene fiber reinforced polypropylene composite. And this is I think at this moment, one of the widest used composites in the world. We might not realize that, but the Samsonite suitcases we developed together with Samsonite in Belgium is having this polypropylene reinforced polypropylene composite, and they produce up to 600,000 of these suitcases every year. So it's a very high volume composite application. Okay, this is the property of this material. A very low initial stiffness, but still 3-4 times higher than polypropylene, so it has an initial stiffness of about 3 to 4 gigapascal, a very low yield stress, but a very high failure strain, and this area here, which represents the energy to fracture, is very high and is the most important design characteristic for suitcases. Now, if you compare that to a woven carbon fiber polypropylene composite, this is the curve here. This is a kind of rather regular carbon fiber weave with a little bit more than 40% of carbon fibers. We have, of course, a much higher stiffness, but a failure strain, as we all know, between 1.5 of 2%, so a very brittle material. And the question is, can we do something in between by combining these two materials? And that was the start of a European project which we had a couple of years ago, where we started from the Samsonite suitcase material and wanted to go in the direction of the 100% carbon fiber composite material, which has something between 40 and 60% of carbon fibers. We know by simple rule of mixture that the stiffness will go up, that the strength might go up, but that's a little bit more complex, but we can expect that the toughness will go down. And the question in that project was, how fast will this toughness go down when we want to increase the stiffness of that material? So there are two approaches. Either you try to stiffen up the self-reinforced polypropylene by adding carbon fibers, or you try to increase the toughness of a carbon fiber composite, which is very low, without losing too much in stiffness. So these are the two approaches, and in what I will present to you today, we will focus on the left part here, hybrid self-reinforced polypropylene composites, where we try to add carbon fibers to increase the stiffness of the material while not losing too much in toughness. Okay, so the first attempts were done, as I said, in the framework of this European project, HYFOCOMP. And one of the things, I will not present the whole project, just two small things. One is that we were weaving into a polypropylene weave, we were weaving into it carbon fiber polypropylene tapes. And we could change the fiber volume fraction or the carbon fiber tape volume fraction in this type of weaves. And what did we observe? Well, we observed that we have indeed a strong increase in stiffness, but at a failure strain of about 2%, the first carbon fiber tapes were fracturing, and then we had a load transfer, and then a second tape was fracturing, and third tape, until all the tapes which were present in the material were fractured, and then we were only loading the self-reinforced polypropylene until its failure strain of between 15 and 20%. So, kind of nice. We have an initially high stiffness material or increased stiffness material, but before it completely fractures, it can absorb quite a lot of energy, and it fractures only at a strain between 15 and 20%. We have been doing different things. We have been weaving them in two directions. And here you see nicely that if we add 11% of carbon fibers, not carbon fiber composite, but purely carbon fibers, we still have this increasing stiffness, a fracture at about 2%, and then we have a certain remaining ductility in the polypropylene, but we lose quite some ductility. And it's only up to 7% of carbon fibers that we can, again, exploit the complete ductility of the self-reinforced polypropylene. And we could indeed make then a suitcase out of this. So this material is perfectly thermoformable and gives you a high-quality suitcase. So what we in fact then wanted to improve after that project, we wanted to avoid this sudden drop in stress at the moment the carbon fiber is breaking. Because this type of instabilities in the stress strain behavior can, in certain practical applications, cause quite some problems. So we wanted, instead of having a higher stiffness and a sudden drop in the stress and then some further ductility, we wanted to have what we call a pseudo-ductile behavior. That at a certain point, indeed, the carbon fiber part in the hybrid start fracturing, but we don't have this sudden drop, so we have a kind of pseudo-ductility. And we have been realizing that by choosing deliberately a cheap preform, namely random carbon fiber mats. In this study, these were random carbon fibers provided by Torre, but we are now also looking at recycled carbon fiber mats, because that could be a way, this technology could be a way of giving more value to the recycled carbon fibers. We studied two layups, a nominal layup where we have the self-reinforced material, for instance, at the outside, and all the carbon fiber mats blocked at the inside, or we can have a dispersed layup, and you will see later on that this plays quite a role. So two materials, as I said, the woven self-reinforced polypropylene on one hand, and a carbon fiber web on the other hand, provided by Torre, with 6 mm long carbon fibers. And so what we wanted to avoid, as I said, is this discontinuity. We wanted to go to a pseudo-ductile behavior. And indeed, we have been able to do that. Here you see the stress strain curve of just a random carbon fiber mat. It has a quite high and that has about 70% carbon fiber. So it's not a 40% carbon fiber mat, it's a 17% carbon fiber mat. So it has a high stiffness, but again, it fractures at about 2% of strength. The black curve here is the self-reinforced polypropylene, and you see that when we are starting to add carbon fibers, 4%, we have a drastic increase in stiffness, drastic increase in yield stress, and up to about 8%, between 7 and 8% of carbon fibers, we seem to have a very nice pseudo-ductile behavior. We have a strong increase in stiffness, we have a pseudo-yielding of the material, and we have then a continuous increase in the stress up to failure strains of between 10 and 15%. That was a very important result, we believe. Stiffness times 3, yield stress times 3, and still having a failure strain between 10 and 15%. We started then playing, and I will not dwell into all the details, we started then playing with, for instance, as was presented in the first lecture, with the interface between fiber and matrix, and the easiest way of doing that is adding maleic anhydride to the polypropylene, so you increase the adhesion, and what you see then indeed is that with a low adhesion you have a lot of pull-out at the fracture surface, whereas with a high adhesion you don't have pull-out at all, which results in an increase in strength of this carbon fiber polypropylene mat. But again, failure strain, as you see here, of only 2%. Does this have an effect on the hybrid behavior? Yes, it does, in the sense that we have a stronger increase in the knee point when we have a better interface between fiber and matrix, And we even can, at a rather high fiber volume fraction, we can have, we find again this peak here, but still we have a very high yield stress here, and then a failure strain of about 10%. This was for a very simple layup. Then we started to disperse the layers, to have different thin layers, and we see some very interesting effects. We see that if we disperse the layers, then even at more than 8% of carbon fibers, we can keep a kind of pseudo-ductile behavior as you see it here. So it would lead me too far to go into detail, and we have been publishing all this recently, but we can now understand where that ductile behavior comes from and when we have a more brittle behavior, and it all relates to the fact that if you have a brittle behavior in the hybrids, the initial carbon fiber fracture is localized and remains localized and leads at the strain of about 4 or 5% to the total fracture of the composite, whereas if you have a ductile behavior, you have an initial fracture of the carbon fiber layer. That carbon fiber layer creates, that fracture creates some delaminations, but there is stress buildup in the rest of the material. You have a second fracture, a third fracture, and finally the whole carbon fiber random mat layer is fracturing and leads to a very high failure strain of about 10%. So, can we model all that? I don't know how I'm doing in time, but 5 minutes, so I will be very brief on this modeling. Yes, we can, of course, model the Young's modulus of the material by a simple rule of mixture, but by a incremental rule of mixture, we can also model the whole non-linear stress-strain curve until the moment that the carbon fiber mat starts fracturing. And we see here indeed by adding carbon fibers we can drastically increase the modulus from about 3 gigapascal for the self-reinforced polypropylene to values around 8 to 9 gigapascal as long as the material remains ductile. The brittle material here, the pure carbon fiber MAPP, has a modulus of between 12 and 14 gigapascal. We have also been able to model the knee point here, and we see a drastic increase of the knee point from about 20 gigapascal to values around between 70 and 100 gigapascal. And we have also developed, but we don't have time, people who will be interested in it can contact me later. We have been also able to predict whether we will have ductile or brittle fracture by using a simple methodology saying that we can calculate easily the stress in the carbon fiber random mat on one hand, and then the failure stress in the remaining self-reinforced polypropylene layers by combining those two. As long as the sigma 2 is bigger than sigma 1, we will have pseudo-ductile behavior. If sigma 1 is bigger than sigma 2, then we will have a brittle behavior. I will not go further on this. So, summarizing all this, what does it mean? Well, we think we have been developing a very interesting material which outperforms, on one hand, polymers in terms of the stiffness, but outperforms all other composites in terms of strain to failure or toughness. And this is even better presented here. Again, we have here this banana-shaped curve. Stiffness now is here, failure strain is here, and this is a whole collection of all different types of composites we have, and we see it's very difficult to avoid these banana-shaped curves. Either you have a high stiffness but a low failure strain, or you have a high failure strain but a low stiffness. What we have been showing in the research and have been reporting to you now is that indeed we can keep the high failure strain and increase the stiffness of a carbon fiber reinforced hybrid composite to values around 10%, to values where we have a stiffness of between 7 and 10 gigapascal and failure strains of about 15%, which is 10 times more than a normal carbon fiber composite. And in new data, which we are developing in the framework of other projects, we are now approaching much higher stiffnesses. We cannot keep this failure strain of 15%, but we have failure strains between 5 and 10%. So we really are able now, with this self-reinforced polypropylene carbon fiber hybrids, to escape this banana-shaped curve. I will stick to this, and I thank you very much for your attention. This whole thing is now applied to Samsonite suitcases. We are also modeling these suitcases. A suitcase seems to be a very simple thing, but I can tell you it's extremely complex to model the fracture and failure behavior of a suitcase, and only now, since about a couple of months, we are able to fully model the non-linear behavior of a falling suitcase, which is, by the way, the test Samsonite is doing for all the suitcases. I just wanted to show these conclusions and to mention all the people who have been involved in this research. Thank you very much.